Okay, you can see that okay?
Yes.
Okay, great. Yes, thanks, Cressy, and thanks to Chris for inviting me to speak in this mini symposium. I'm going to be talking about some work that I've been doing here at Exeter with Cressy and Pete that's been funded by the EPSRC to start with, and then the Medical Research Council more recently. So the motivation for my talk comes from phenomena that are observed in recordings of sequential activity in neuronal populations in cortical dynamics. So I've got a couple of examples shown here. There's quite a lot going on this slide, but basically what I'm interested in are transitions between different brain states where there are groups of or populations of neurons that undergo sort of collective behavior. And so one example here is from anesthetized rats, and what it shows are two different states, so a down state and an up state. And the down state is this quiescent kind of quiet period, and the up state is a massive persistent period of activity where there's this big sort of surge of activity that's transient, and then it shuts off again and goes back to this down state. And if you zoom in at the transition from the down to the up state, we get a picture that looks like this kind of cascade here, where the red represents the active up state and the blue is the down state. And you can see there's this domino-like sequential activation of these different neuronal populations. And my other example that if you've seen my talks before, you know I like to give epilepsy as an example. And so here I'm showing 3 spatiotemporal patterns of seizure onset. These were recorded from the same person with epilepsy using ambulatory scalp EEG recordings. And we can see that there again are these domino-like cascades of transition between the sort of normal brain state and the seizure brain state. So these examples represent transitions between, you can think of these as transitions between different attractors in networks of bistable nodes. So you'd have that the seizure state and the non-seizure state are both attracting states, and you get this transition between them. And the way this activity propagates in these examples is not fully understood. So I also like to think of these transitions, and what I've been thinking about more recently are transitions and changes in synchronization that are associated with these transitions. So this first example here, these are recordings from the prefrontal cortex of freely moving macaques, and they are interested in periods where of just sort of general wakefulness and what's called wakeful rest. So they're just sort of sat daydreaming. And we can see that they transition between these states. And when you look at the synchronization of these states, you can see that during the wake state, there is more desynchronization. This synchronization index that they computed is generally lower. And during rest, there is much more synchronous activity. And the same sort of thing is true if, again, we look at the example of epilepsy. This case is looking at hippocampal recordings. And these, we can see that the seizure is detected on different electrodes embedded in the tissue as the seizure is initiated. Again, we've got that nice cascading activity that we saw before. And now if we look at the synchronization index, we can see that the synchronization changes as electrodes or neural populations are recruited to the seizure state. So I'm interested in trying to characterize this sort of dynamic synchronization and trying to contribute to understanding it better, which might then feed into a better understanding about sort of the initiation and propagation of seizure activity in epilepsy. So networks and transitions have been studied before. There's a large literature on them that I've not done justice to here. I've just listed just a couple of examples. First, of noise-induced transitions on networks between either symmetric bistable nodes or asymmetric bistable nodes. So the asymmetric bistable nodes will be where one attractor is much more stable or strongly attracting than the other, which might be a metastable state, for example, that you could easily escape from. And I just highlighted some of our previous work here, where we look at how networks of asymmetric attractors, asymmetric bistable nodes, change as you change the coupling strength of the network, and the partially escaped states, your options are much more limited as your coupling gets stronger. There's also been some work on looking at changes of synchrony in the case of absence of noise, and the work by Azad and Ashwin. So here they couple two elliptic Barton type bursters, and you can see that there's a change of synchrony that's not induced by noise, but is perhaps a feature of the complex coupling that they've used in this case. But this feature has actually also been shown to be robust to different sorts of coupling, more neurologically feasible, such as synaptical gap junction coupling. That's the work by Sherman. So these things have been looked at before, but to our knowledge, changes in synchronization during sequential escape or sequential transitions have not been previously investigated. So that's what I'm going to talk to you about today. And the model that I'm going to use may be familiar to some if you've seen me speak before. So this is just going to be a network given by this system of stochastic differential equations here. My nodes are going to be governed by this Barton type normal form. So it's sort of like a generalized Hopf normal form, if you like, where we have additional phase parameters in this eta and delta here. The bifurcation parameter in this case is our new variable here. And so for the noise-free dynamics, I've shown the bifurcation diagram here, where we can see that the unstable equilibrium is stabilized in this Hopf bifurcation, and that we get this unstable periodic orbit and stable periodic orbit. And so this is region of bistability is the one that I'm interested in. And I'm going to fix my parameter nu at 0.2 throughout. So we're going to have this asymmetric bistable attractor, and I'm going to be starting all of my realizations of the full noisy system at the equilibrium and looking at the transition to the oscillatory periodic orbit. Those transitions are going to be driven by noise that I've added on here. This is additive white noise, and it's governed by the amplitude alpha. And the coupling that I'm going to be looking at is given by the adjacency matrix. I'm going to be considering all-to-all coupling. I'm going to be considering 3 nodes in my examples today. And the coupling function, I'm going to take you through 2 different coupling functions, or one coupling function and a modification of it, if you like, and explore how the dynamics change. I'm fixing my noise amplitude throughout as well. So what I'm going to be changing are the coupling function and the coupling strength. That's what we're really going to be focusing on here. So a little bit more on just the single node dynamics, just to set things up a bit more. So this is the single node system here, and I've plotted the equilibria, unstable periodic orbit, and the stable periodic orbit in these plots. Here we have the time series with one realization, which is shown in black. And if we use the standard Ito transformation to convert this system into polar coordinates, we can identify the amplitude of these different values, these family of periodic orbits here. So like I said, I'm interested in transitions from the equilibrium out to the periodic orbit, and due to the asymmetry in the system, I'm not going to look at transitions back again. So the timescale of transition back is going to be much, much greater than the things that I'm going to be looking at today, so I'm just going to ignore them. So what I'm interested in is this escape time idea. So this is a classic way of characterizing this transition. So we're going to look at how long is it going to take for our realization that we start at 0, simulate with a classic stochastic Hern method, and how long is that realization going to take to cross some threshold that we choose here, and given that we've started at 0. So I've chosen this threshold to sit in between this unstable periodic orbit and the stable periodic orbit, so that we don't get any false transitions in the numerics. Like as soon as we've hit this threshold, the only place you're going to go is this stable periodic orbit. Because this escape time is a random variable, we can define its expectation, so we can calculate the mean escape time. And for the single node, this is well characterized, it's well known, and can be identified using the Irwin-Kramer's escape time, which gives you an asymptotic expression for the mean escape time as the noise tends to 0. So I'm not going to talk any more about single nodes. It's been well characterized, and in our previous work, we have looked at the single node in more detail as well. So let's move on to generalizing this idea to networks. So we can look at the escape time of the ith node in our network. This is the time that it takes for that node to cross the threshold that we've given, and we're going to have the same definition of the threshold that we did before. So, but now, because we've got multiple nodes in our network, we're going to have a sequence of escapes. And so what I really want to know is how long is it going to take the first node to escape, the second node to escape. And I don't care if that's node number 1 or node number 2. It could be node number 24 for all I care, but it's going to be the first and second that I'm interested in. Because then I want to look at this, what I've called a conditional escape time. So given that, say, 2 nodes have already escaped, how long is it going to take the third one to go? So it's these values that I'm going to be exploring numerically and simulating. So this is a random variable as well. So again, we're going to define its mean and its expectation like this. So the first type of coupling that I'm going to be looking at is amplitude-only coupling. So it's going to have this sort of form here, such that when we convert the system into polar coordinates, again, assuming an all-to-all connected network, we can see that the coupling only pops up in the amplitude part of the polar coordinates. In particular, I'm going to use this form here. So this is a nonlinear coupling function. It's governed by the coupling strength C. This is what I'm going to be changing. And we've chosen this specific form of coupling so that it only affects the nodes that have escaped. So it only affects active nodes. And if we look at the amplitude coordinates, we can take the noise-free case, and in the same way as we did for the single node, we can identify the amplitude of the periodic orbits. And in this case, we can see that it depends not only on the parameter nu, but on the coupling strength, as we would expect. And because I said the coupling only affects active nodes, it depends on the number of nodes that have already escaped. So to look at how this amplitude changes in the noise-free case, we can look at the bifurcation diagram. So there's quite a lot of curves going on here. So this is for a 3-node all-to-all connected network, and C equals 0 is the disconnected case, where the amplitude of all 3 escaped states is the same. Here, the key is the number of stable eigenvalues or stable Fourier multipliers in the case of the periodic orbits. So here, so the blue lines is what I want you to look at the moment. So we're going to start, there's always going to be a stable state at the origin at this equilibrium, which is what we're going to escape from, sorry, that's where we're going to start. And then we can see that for the disconnected case, all of the partially escaped and fully escaped states have the same amplitude, whereas when we increase C, this curve here, there's actually a blue curve lying under this one as well. And what this shows is so that this is when 1 node escapes, the amplitude will be here. When 2 nodes escape, the amplitude is going to be here. And when 3 nodes escape, the amplitude is here. So we can see that the amplitude is increasing as more nodes escape. And conversely, on the other side, we can see that for 1 node to escape, 2 nodes to escape, 3 nodes to escape, we get this decrease. And actually, you can see that these stable states disappear in a series of bifurcations here, so that for C large and negative, or relatively large and negative, I'm only looking in very weak coupling regimes in this case. So here we actually have that the states where 2 and 3 nodes have escaped and are no longer stable, they've disappeared, and so we can only ever have 1 node escaping at a time. So we can summarize this information by computing 1,000 realizations for fixed C value and seeing what the escape times are and computing the mean. So each point on this curve is the average over 1,000 realizations. And we can see that the escape times for the second and third node to escape decrease for C positive and increase for C negative. And this is also encapsulated in these distribution plots, these violin plots that I've got here. So for the first node to escape, given that none have, for the second node to escape after one has, for the third node to escape after two have gone. We can see that as for C positive, these are just snapshots from here, that as C is positive, we have this speed up of this sequential escape. And so we're going to call this an accelerating domino effect. And for C negative, we have the opposite case. You can see the escape times get very, very large. And so what we have in this case is a decelerating domino effect. So that's the behavior for the amplitude coupling case. So now I'm going to add on phase as well, because I'm interested in this interplay between phase and amplitude. So here we have the same amplitude coupling that we saw before, but now I've added on this phase component in the same spirit. So again, it's only going to affect the active nodes, and I'm only going to be changing the value of the strength of this amplitude component, which is epsilon. So I'm going to be changing epsilon and C and seeing what happens to the dynamics. And in the polar coordinates, we can now see that the coupling influences both the amplitude and the phase dynamics. So the way that the classic way, and Kevin spoke about this in his talk as well, is to look at the order parameter if you want to characterize phase. And so I'm going to look at the order parameter between the nodes that have escaped. And if we do this by looking at the moment at which the realization escapes, so here I've plotted one realization, you can see node 1 escaping, node 2 and node 3. But if we look at the order parameter here for the first and second node to escape, you can see this, and in fact the third node to escape, it's very noisy, and there's a slight drift as this order parameter kind of stabilizes. So what we're going to do is we're actually going to take the order parameter a little way into the realization. So in particular, I'm going to calculate the order parameter for two nodes to escape at this point in between the second and third escape, and for all three nodes to be, it's 1500 time steps after the third escape, just so we get that level of stability. And so what does this look like for different values of epsilon and C? So here I'm varying my C value. This is the amplitude coupling, the strength of the amplitude coupling component. And so we can see when it's negative, we get this decrease in amplitude of the periodic orbits. And when it's positive, we get this increase in amplitude, as we saw before. And now if we look at the phase parameter, so here the amplitude of the phase coupling is positive, and we can see that in each case the nodes tend towards stability when all three nodes have escaped. So one here is obviously the synchronous state. For epsilon negative, we can see the opposite pattern basically. So we see that nodes tend to anti-stability as all three nodes escape. So we get this sort of asynchronous regime here. In the same way, because this order parameter, as we've defined it at these specific time points, is still a random variable, so we can also define its expectation and look at the mean order parameter, I sometimes call it mean phase, as well as the mean escape time. And so here I'm plotting the mean escape time and the mean order parameter in purple against this C, as we saw before, for different values of epsilon. And we can see the same pattern that we saw before with the escape times. So we can see this accelerating domino effect for C positive and decelerating for C negative in each case. And we can see that for the order parameter, we get the tendency to asynchrony, so the anti-synchronous state for epsilon negative, and to the synchronous state for epsilon positive. So what would be really cool is, well, can we get a switchover? And the answer is obviously yes. So if we, so what do I mean by that? So if we look at, we've chosen C minus 0.4, and I'll tell you why we chose the specific value in a second. But what we can see is, first of all, that the realizations have got very long. I've actually broken the axis here. But for the first, so for the second escape, the order parameter is very, very close to 0 here. And then when all 3 nodes have escaped, it pops up and it tends towards a more synchronous state. And the opposite, that's for epsilon negative. For epsilon positive, we get the opposite effect. After the second escape, the 2 nodes that have escaped are in sync, and then they go out when the third node has escaped. And we can see this really nice crossover in our mean order parameter values here. So very quickly, I will just tell you how we picked our value of 0.4. And so in this case, we were able to, due to the nature of the coupling that we chose, it's quite a nice function, we were able to do a bit of analysis on the system and look at the stability of the partially escaped in-phase solution. So we can work out when this is stable. And basically, it's an interplay between the phase and the amplitude dynamics. So we can visualize this by looking at the phase dynamics of the single noise-free node, and we can identify the change of shear near the periodic orbits, which is plotted as this orange point here. So this is, I'm plotting omega against r here. And if we look at the sign of the slope of the phase at the escape amplitude, what we can see is that at c equals minus 0.4, we have a change in the slope, which gives us this change in stability. So for 2 nodes to escape, we see the slope here is negative, and for 3 nodes to escape, the slope here is positive. So I will leave it there, and the take-home message from my talk, I guess, is that these sequential escapes and the interplay with synchrony I find really interesting and have very nonlinear dynamics. So I've shown you an example of this where we're able to characterize this change of synchrony using this idea of mean escape time and mean order parameter. And I will leave it there and answer any questions you have. Thank you.
Thank you, Jen. We have an attendee that has raised their hand, and I will allow them to talk. Perhaps they want to ask a question, I would imagine. So I am allowing you to talk. Can't pronounce the name. Kestutis. Maybe they have raised their hand by mistake. So there's a question by Istvan Kiss. Would the behavior be similar with classical Stewart-Landau oscillators?
Oh, that's a good question. To be honest, I haven't looked at the classical standard Stewart-Landau oscillators. I guess what you need for this, we did choose our coupling functions quite carefully for this. So if you can get that transition between the different states, here we chose a system which has the oscillatory state and an equilibrium state, but it's the coupling that helps to really induce these dynamics. So it would be really interesting to extend these ideas to look at different, coupling different oscillators together with the similar sort of coupling functions, and I would expect a similar sort of thing to happen, but the patterns of escape times, the exact properties, so this accelerating, decelerating, it should be pretty robust, but I don't know, it would be interesting.
Thanks. One more question. Thanks for the nice talk. Could you please comment on how the parameters of the model might be related to physiological parameters of neurons?
Oh, yes, that's a good question. So in this case, I think the simple answer is that I can't, because this is a very idealized model. I mean, it's a classic Hopf normal form model, and this phenomenological idea has been applied really nicely, especially in epilepsy analysis, to study and try and sort of predict and understand how you get the transitions between different states. And I've looked at how you can use this to try and tease out some of the details of the seizure onset patterns. But I think this sort of relates back to the previous question, where actually it'd be great to take more realistic neuronal models where we can actually identify the biological relevance of these parameters in a much more concrete way. Like I think here it would be perhaps a little bit clutching at straws to try and make any direct comparisons. I'd be very wary to, but I would absolutely, the next step definitely would be to couple together more biophysically realistic neuron models and see what sort of behavior we get, and also expand it to larger networks, which would obviously be more realistic again as well. And I think that would be really interesting too.